Welcome everyone to the IFML seminar, and it is a pleasure to introduce Micha Livne. Micha did his undergrad at the Technion in Israel, and then he did his master's and his PhD at University of Toronto, studying under Jeffrey Hinton and alongside Ilya Sutskever, if you've heard of them.
No.
And then he, after some postdocs, he is now working at NVIDIA. Not in building GPUs, but in NVIDIA's sort of in-house AI research. And he's going to tell us about building generative and discriminative learning with contrastive mutual information machine. That's a long title.
Yeah,
all right, I look forward to finding out what that means.
Thank you. Thank you for the kind invite.
Sorry for the unusual configuration.
Yes.
Seating there. I don't know how
Yeah, I think that they mentioned it, but no, it's all right. Okay, so thanks for having me over. Just one correction. I did my postdoc under Jeff. My PhD was under David Fleet, but everything else is correct.
Okay.
All right. So yeah, just a little bit about me. So I'm right now in a digital biology research team for the past few years, but my background is fundamental machine learning. And today I'm going to talk about the application of basically a learning framework. It's a symmetric variational autoencoder that I've been working on it for a few years. So it's a line. The research described here is spread across a few years. The high-level motivation would be, for me, is to enhance control and interpretability in generative models. And there are a few key challenges in generative models today. By the way, I encourage you, if you have any questions or comments, please let's do it interactively. I find it more engaging. We can also wait to the end. So first thing is alignment. So controlling the outcomes of a generative model, still hard, we all know it. And then I was looking to get like a scheme. Basically, I thought I want a black cat within an hour to a white cat. And I got that and realized it couldn't have been any better. So this is definitely not what I had in mind. And it's an alignment problem. How do we do that well? And second thing is to balance interpretability with model expressiveness. So we know that for a model to be powerful, it has to be very expressive. Then the question is, how can we understand maybe the internal processes of what's going on inside? I lean towards, more towards, I would say, mechanistic interpretability or maybe concept-based, analyzing high-level features of the model. And today I'm going to actually talk about a system that allows that. And finally, integrating direct data modeling with some flexible latent representations. And by that, I mean, I'm going to talk about it in the next slide. But for instance, when you generate an image from text, you need to embed the text. So how can you learn the right representations in order to get alignment and maybe interpretability? And my research focus, I'm going to touch about all of these 3 points today. I will show a system that allows controllable generation. It's going to be for small molecules in that case. I'm going to talk about how to learn embedding that are useful for downstream tasks, informative, and also have some inherent structure that is beneficial. And finally, I'm going to show that you can actually unify. You can have a single model that is doing both the generative part and the discriminative part. All right. So let's start. Diffusion models took the world by storm. I think in 2015, there was the initial paper. Around 2017, 2018, suddenly crazy, beautiful images started to pop out. And they're doing great, but they still have a few issues. First one I would say is that it's working on a fixed dimensionality. So you need to know the number of dimensions before you generate it. Let's say that I want to sample a molecule. I need to know the number of atoms before that. So it makes it a bit awkward. It's not a joint modeling. The second thing is that to get high quality samples, even today, it takes multiple, many times, many, basically diffusion steps to get what we want, even though we have advancement in distillation. So that's a work in progress. Discrete diffusion models are still lagging behind the continuous ones and also autoregressive discrete models. Now the gap narrows. I'm not sure if anyone heard about the Inception AI. It just, I think 2 days ago. So it's the first commercial diffusion language model, which is pretty cool because it generates the whole text jointly together. It's okay. from the quick test I did, it's still not a state of the art, but it's getting there. And finally, if you really want to go to high dimensional data, it gets expensive, both from memory and computationally. So even though latent variable models, which used to be this thing in like 2014, we had VAE, we had GAN just developed. It was very exciting. It looked like it was pushed a bit to the back when we have those monolithic gigantic priors, basically like autoregressive models over text or diffusion models. But I'm going to claim today that actually they never left. They're still here, and I encourage others to further explore those. So latent variable models, the first thing that they offer is a unified framework. So it can handle variable size, it can handle continuous and discrete data, projecting all into a fixed size representation, the latent code, which is nice. That's sort of, let's say, an online embedding instead of just having a fixed learnable embedding. It allows us to facilitate some hierarchical representation. So anyone is familiar with a large concept model from Meta? It's a few months ago. It's a very cool paper, basically showing that you can train an LLM to operate in the latent space of an encoder-decoder of words. So it basically operates on the latent space of sentences. And you get some interesting properties with that. It allows efficient sampling and generation. So if you have the encoder-decoder, the latent variable model, the diffusion can operate on that space. That's latent diffusion model. And then finally, it also provides a natural condition for generative processing. And I'll be specific. What should we use when we train text to image? Should we use Clip like DALL-E? Should we use T5 like Imogen? Each of them has different properties. Is there any principled way to do it? So it's an open question, but there is a lot of questions to deal with. All right, so that's the introduction. This is going to be what I'm going to talk about. I'm going to introduce the mutual information machine. That's a symmetric variational autoencoder. Relates to VAE, shares the same architecture. I would say it's in the realm of autoencoder, VAE, and you've got cMIM. I'll contrast it a lot to VAE and autoencoder because those are the closest model. And then I'm going to talk about two case studies. First one is controlled generation of molecules, lead optimization to design basically new drugs. And the second one is how to incorporate contrastive learning into the model. And I would also end with an interesting, that was a byproduct of this research, that could be actually useful for everyone. That could be a freebie if you have encoder-decoder, how to get more informative embedding, which I termed informative embedding. All right. Any questions, comments so far? Okay. By the way, I didn't add too many equations. I find it in such a talk, it's really hard to dive into the math. Some of you might find it more interesting than others. So either ask questions or you can talk about it at the end. There are a few equations because that's what makes it tick, but this is mostly a high-level overview, discussion of the concepts and the principles behind. Okay, so MIM, the mutual information machine, and you would have all of the links on the presentation at the bottom. It has three core principles. First is high mutual information between the observation and the latent code. So the latent code is informative, which makes sense. If the latent code is non-informative, it's not a very good representation learning model. Second thing is clustered latent representation. So similar samples would be positioned nearby in the latent space. And the third one would be symmetric encoding and decoding distributions. And this is unlike VAE. Anyone here is familiar with VAE? Just to make sure that I'm a little bit. All right. So in VAE, we've got the generative model. We have P of Z and P of X given Z. That's our model. We would like to be able to encode it. We would like to get P of Z given X, but we don't have that. So we're going to learn an approximate encoder Q. So it's not a symmetric treatment of the model. In MIM, it's actually symmetric. So the model has both the decoder and the encoder. Both are trying to approximate the joint probability, the undirected version. So this is where the approximation happens. And there is complete symmetry between ZX, the encoder, and the decoder. And in fact, if you just ask symmetry from a latent variable model, that's enough to break down into the core three principles. So it's pretty cool that one principle actually breaks down to all of that. Okay, so what is it? This is going to be probably the heaviest math in the whole presentation. And then I'm going to talk a bit about the implications of training a model as I'm going to describe, just to get intuition, and then we'll get to the example. Any questions, comments so far? Or all right. So that's our model. We have a model decoder and a model encoder. We're going to define our model to be a mixture model between the two. If you'll notice, everything here almost is going to be symmetric. Our sample distribution can also be symmetric, but typically it's going to be the anchor P of X. We don't have that. We only can draw first samples of it. That's a data set. And then the joint distribution is using the same posterior, the same encoder. This is actually identical to what you would use in VAE. And the learning is pretty straightforward. So if you take the average between the cross entropy of our encoding distribution and the sample distribution, and the decoding distribution and the sample distribution, you could go to the paper and see that this is an upper bound on that expression. So when I minimize that, I do three things. One, I'm going to minimize the marginals. Now, the marginal of X is fixed. We don't control it, but the marginal of Z, we learn it. So it's going to create clustering or low entropy. The second thing is going to maximize the mutual information between the two. There is one other thing, which is actually very cool, but I'm not going to talk about it right now. There is another hidden step here. There is a very strong regularizer that makes sure that P and Q are going to be the same. It's like an autopilot. If you take the gradient, every time they're not the same, it takes very aggressive measure to actually keep them together. And in practice, that's what you're going to do. You're going to minimize the sum of the log probabilities. So this is log over everything. So it's basically log of Q of Z given X, log of Q of X, plus log of X given Z, log P of Z. Very similar to the VAE. VAE just have also a minus sign. If I'm going to put a minus sign on the posterior, you sort of get VAE. There is stable training, similar to VAE. There is no hyperparameters in the loss, which is, I would argue, unlike VAE, due to posterior collapse. So anyone here is familiar with posterior collapse? Yeah. I'll repeat it. So the problem with posterior collapse when you train a VAE, VAE was actually never meant to be a latent representation learning model. It was devised by physicists in order to solve the inference problem. We want to evaluate log P of X. That is just there to help us to do that. So if you have a very powerful decoder, it doesn't actually need information from the encoder, and the encoder can, or the posterior can very, very comfortably just converge to the prior. So if you have P of Z, there is no information from X. We need Q of Z given X. So it doesn't suffer from it. And similar to VAE, it uses the reparameterization trick that allows learning with high dimensional data. I'm going to say the last technical thing about it. In practice, what it means that we're going to get unbiased, low variance gradient estimator, when we're using gradient descent. So it's very easy to train. Yeah.
Can I ask some clarification questions?
Please go ahead.
Okay. So I think of X as being an image in pixel space and Z being like a little vector, right?
Correct.
So Q theta is the encoder which takes pixels to vector.
Yeah.
Right. And so I understand what is Q theta of Z given X.
Yeah.
What is Q theta of just X? What is that?
Very good question. And I'm happy that some people here are actually reading in it. You can actually train a prior, like over the data distribution. In practice, we don't want it because it's expensive, right? So the nice thing about me, because everything is positive, we're going to make that to be the expectation over P of X given Z. You will see in the loss, when you actually present the loss that I train, I never actually compute that. I basically force that to be the expectation over the decoding distribution when I take the expectation over Z. That's how I compute it. And because MIM has all of the sign is the same, it's very easy to actually upper bound, the upper bound, the upper bound. It makes it very easy to actually do those kind of tricks. We can talk about it later or dive deeper in the paper, but it's a very good question. So you're absolutely right. In practice, we don't want to do it. You can if you choose. So this is just a generic view, but it's a very good question. Any other questions, comments? All right. So this is the math, but let's talk about the intuition. So what does it mean? All right, so you train that, it looks a bit like VAE. Under some circumstances, you can change just one sign from minus to plus and you switch from VAE to MIM. So first intuition, I will show you this just high-level example. So let's say that our observations are 2D. So we have two mixture models, two Gaussians. From each of them, I'm going to draw two samples, the red and the green. let's start with autoencoder that basically takes our observation, project it into 1D space, and then reconstruct it. We have no regularization on the latent codes. So that means that you're going to get typically higher entropy. So the 2 points might actually not be near each other on the latent space, but reconstruction will be good. That's the only thing that the model is doing. If you compare it to VAE, in VAE, we do have heavy regularization, so we get the order. The size of each ellipse here would be the variance. And you could see that it's getting pretty blurry. That's what you get with VAE. That means that when you sample from the middle, it's unclear where it's going to go. In images, it's going to look like a blurry image. In text, you just get nonsense. That's one of the reasons why you don't see almost any VAEs for text. But MIM is actually shining with that. Molecules here is actually text. This is based on sentence MIM that was for text. MIM would be somewhere in between. So you do get good reconstruction, so very small variance. In fact, when you train, you have to limit it, the variance. It's not part of the loss, part of the architecture. You have to limit it not to get into infinity, because it will try to get the best reconstruction that it can, but you also get the order. So that's sort of intuitively. And the second thing is, this is an example from MNIST. So identical architecture. I only changed the loss. This is MNIST. So I train it unsupervised on MNIST, and then I take the test set. I project all the points into the latent space, and I color it. This is for us. The model has never seen it. This is what you get with VAE. So that blurriness is exactly the partial collapse, and it's trying to sort of match a Gaussian. That's what we asked it to do. Every place where you have the mixing between, let's say, the red and the yellow, that would be either wrong classification or just bad generation. And MIM looks like that, an identical architecture. So it's heavily clustered. Similar, looks a lot like contrastive learning. Contrastive learning is also very clustered. Okay, so that's about the intuition about MIM. Any questions, comments about that? Makes sense? Yeah, go ahead.
To comment about the symmetry there, if you go back to the previous slide.
Which actually we have the symmetry, you can see it here. This is a good one.
Yeah, yes, if you go to the loss, which
Oh, in the loss? Okay. Yeah.
the loss is not symmetric about P&Q.
Oh, it is. But P&Q, it is. The only lack of symmetry here would be in the sample. Yeah. So this is why very, very good observation. MIM is actually, this is also a mixture model. This is a simplified version. And when you actually train a full MIM, it includes both generation and encoding. So you sample both from the model and from external sample set. And then you get the full properties. You're absolutely right. This is what's called AMIM. It's the asymmetric version of it. That's the only symmetry that was broken here. But very good observation, and you're absolutely right. But everything else, if you look at it, it's complete symmetry between the two. The reason why I removed it, it's for practical reasons. In many cases, you don't want to sample your model. So it still works. However, if you actually want to get the full model, and I would argue, even today with LLMs, to get an LLM to generate what you want, it's not enough to be passive, just to watch. You actually have to have samples as part of it, RL. So MIM gives a different twist of why would you like to have the sampling on the name of symmetry. But you're absolutely right.
If you were to train a symmetric MIM, it would have samples from both the model and as well as the training.
Yeah, exactly. Exactly. When you train for MIM, and it works well. Just typically for autoregressive text models, it's just too slow. So you can also do that, but it works well. If you also sample from a discrete distribution, you need to, you're doing reinforce, right? So you can't actually push the gradient into the expectation because your distribution changes. So there are a few aspects to it, but generally speaking, yes. Yeah, good, very good comment, and it works both ways. Okay. All right, any questions, comments about that? All right. So we're done with that. We're going to start talking here about why is it useful? And to me, maybe the biggest two things. I want to introduce you to that. I think it's a very useful framework. I also want you to encourage, not everything is solved. So if you actually identify a few holes or opening in the research, there is a lot of research to do, even though today everyone is just doing bigger and bigger diffusion models or just training bigger and bigger LLMs. Okay, so the problem is called lead optimization. How can I generate a molecule that's not toxic, that's water soluble, is highly likely to be a medicine, binds to this protein, it doesn't bind to that protein. So it's a hard problem. The combinatorial space of all possible atoms is huge, but the actual valid molecules, it's a very sparse space. So latent variable model is actually perfect. It's going to take that sparse manifold and project it into hopefully a dense latent space. And the solution was we're going to use MIM semantically organized latent space. That's how it looks like. So it's an encoder-decoder model. We're going to take, this is called SMILE. It's a string representation of molecules. It's a 2D graph, basically. We're going to push it just like a language model through embedding into a perceiver encoder. Anyone here have heard about perceiver? All right.
Is this a model that like takes the same input again and again through cross-attention?
So the biggest, it has that part, but the biggest thing, it can actually project variable size input into a fixed size. Fantastic encoder, my weapon of choice. Go read it. It's by Aurel Vinyals from like a few years ago. I'm surprised that not more people doing it. Basically use cross attention to project into a fixed space. Fantastic. But any encoder, you can use bridge projection by Yoshua Bengio. Whatever it is, project it into a fixed space. Now we're going to learn informative, high mutual information, and clustered latent space. And then we can push it into the decoder. We're going to sample from the posterior. It's going to be a Gaussian. And then we have the regular transformer decoder using cross attention. We're going to decode it. There are a few contributions in that paper. We actually exploited that. And interestingly, I'm going to show you that the clustering here, even though we didn't use any chemical information or any biological information, it actually clustered the molecule in a chemically meaningful manner. The second thing is we actually mitigated holes. So in almost all latent variable models, you're going to have holes. Let me define a hole.
What's the problem? Are you trying to design a binder for a protein, or what do you?
Yeah, exactly. For instance, design a binder for a protein. So this is late optimization to design a small molecule to get the effect that you would like.
Right, but where's the protein being encoded?
So the protein here would be hidden here through the oracle. I give you a molecule. You need to be able to give me back a score. In that case, it might be simulation of that molecule in a protein, for instance. It could be you pre-trained.
Right, but people generally just do search. If once you give me the score, people just search. I mean, you know.
So the question is how to search.
Yeah.
And it's still not an easy problem. Even if I can give you an oracle, it's still not an easy problem.
Sure.
Because it's a very sparse and high dimensional space.
Right, but I'm saying like the more modern methods would, encode, something about the structure of the protein, like, the backbone.
So everything that you mentioned would be hidden. I'll talk about it soon in the oracle,
Okay.
in the optimization.
Okay.
So this model, so far you're asking me, you didn't do anything chemical right now.
Yeah.
Why would it be better? So I would say, we actually have a lot of tests. This model beats all of the more modern. It's pretty modern, I would say. This is like 2 years old, but we actually had it tested in labs and it works very well.
Okay.
I'll soon explain you why. And the interesting thing to me is that some principal statistical method could actually address.
Okay, but just to be clear, in that scenario, you're just doing black box search. Like you have the
Correct.
optimization function, you're just looking.
Correct,
searching
absolutely,
for it.
absolutely.
So it doesn't have to necessarily be biological or anything, you literally are doing.
Absolutely correct. My claim is that this is a latent space that lends itself to such a search.
Okay.
That's exactly it. You're absolutely right. Okay, so the first thing we wanted to mitigate holes. That because we want the search to be very efficient. We don't want to get invalid molecules. Let me define a hole. High likelihood of the prior and low likelihood of the posterior. So if I sample from that, you're going to get basically invalid sample. And so we did that. That would be, by the way, another example of how you train it. Not that's different from VAE. We sample X from the data set. We sample Z from the posterior. We also sample here the variance. We don't learn it. So we actually make sure that the model can handle all variances. And then you just feed it to the loss, who asked me about where is Q. So here you could see that there is different values. The reason why I have half here and not half here is due to the expectation. Over instead of Q of X, I'm basically taking expectation. And that's it. That's what we do. And then the search itself is a zero-order optimization with a pretty solid baseline. It's called cMIM, covariance matrix adaptation. You can think about it as the poor man RL, where some clever people devise the policy. You don't learn the policy, but given a batch of samples and then a score or a word, it's going to adapt the covariance matrix for the next round of samples to increase the score. So that's what we're going to use. And this is where the information regarding the protein, for instance, would fit in. All right. So first thing that I want to point is, why is that important to have such a clustered latent space and informative? The informative part means that I get good reconstruction. I have very good control of the sample. The clustering part means that I can actually do tiny perturbation. So if I start from this molecule, project it to the latent space, there is a point that I can perturb it, such as only the chirality of one atom will change. Chirality would be right-hand side and left-hand side coordinate system. So you basically flip the direction of one atom. I'm sorry if there are anyone who is actually professional in cheminformatics. That's sort of my computer science depth of understanding. But that's the smallest change that you can make. And we couldn't get that with VAE. It's just not easy to control. We couldn't get with autoencoder because the entropy, it's very noisy. So it's hard to find it. And if you move further away, you can see that I can make, this is the similarity map between the two, mostly similar, and that's just slightly be different. The interesting thing is that this actually translated to a chemically meaningful search space. So what you see here, we took two molecules, the statistics of them, we projected them. So we have Z0 and Z1. Then we take 10 steps. And at each step, we decode it and we check how similar the decoded molecule to the original molecule. And we use what's called Tanimoto similarity. That's a standard similarity metric that's considered to be chemically meaningful. So anywhere between 0.95 and 1 is very similar. 1 is identical. 0.75 is pretty different. And pretty much all atoms in the world are like 0.25. So if I'm going to compare, we compared MIM, VAE, same architecture, just VAE, and same architecture, but without regularization. So a perceiver BART, basically, just an autoencoder. Let's start with the autoencoder. The autoencoder, like I said, has very high entropy. So it's very hard to control. Both the variance and the similarity are not great. VAE is smooth, but it's pretty far. It's hard to control. And you can see that MIM at the first steps keeps very close. That just makes the optimization, regardless of what I'm trying to do, I can take small step. We know that it works because that's how gradient descent works. How do I get into a complex place? Take one step in the right direction. So having a clustered representation, regardless of what we're trying to do. And we tested it, including binding affinity to proteins, including exactly everything that you said. Where is the chemical knowledge? In the oracle. Companies loved it because we don't even need to know the oracle. And the second thing is that it's actually very efficient with samples. And I'm going to continue to the next slide. Any questions so far? Yeah.
So when you say you mitigate holes in the posterior distribution, are you saying the latent representation doesn't have holes, or that the way you search avoids holes?
So we literally mitigated the hole. So it's not guaranteed, but in practice, the way that we train it, because we don't learn the variance, we actually sample from it. The model learns that anywhere from the prior should be valid. If you try to do that with VAE, you will get the father of all posterior collapses in the world. But VAE MIM, because it tries to maximize the mutual information, is resilient to that. I actually like better what you said. In following up research, I'll talk about it. RL will do just that. Instead of trying to mitigate the holes, you can train an RL agent. If you have enough structure in your latent space, the agent could explore efficiently. I actually think it's a better solution, but it's a good question. Any more questions, comments? All right.
I could also the motivation behind learning this latent space set is just interpretability, or you are like you're manipulating it during training or during inference so that you can come up with the better molecule formulation. What's the motivation behind this? Just this learning this set space doing, because you could have learned it any other way, like not.
And people do learn it in many different ways.
Yeah.
I believe that this would actually, to me personally, I wanted to check if the latent space lends itself to RL, and this is like CMA, yes, I call it a poor man RL. Following up research actually validated it. To me, that's my personal thing. The reason why it conducted in the case of small molecules, because there weren't any good solutions. And even today, this model pretty much beat all benchmarks that we have, and we let companies now decide how good it is for them. But that was the motivation. It's not an easy problem how to search effectively and efficiently in such a sparse, high-dimensional space, which is all combination. Like, let's say you have up to 150 atoms, so it's the number of atoms to the power of 150. That's your space. Inside of that, you have a tiny, tiny manifold of valid atoms, and within, it's a tiny fraction of actually atoms that are interesting to you. So it's a pretty hard problem. So did it answer the question? All right. All right. So results. It achieves SOTA performance on multiple benchmarks. That's probably not the place to discuss it, so I'm not. However, it did demonstrate high sample efficiency compared to the baseline. And I'll give two reasons for it. cMIM is a zero-order optimization. It's going to suffer heavily from the curse of dimensionality. So smaller dimensions in the latent space would be better. So this is what we train. This is a mega mole BART. It's just a BART, variable size. You can't really search the space. That's why you want to have a fixed space. Now you can actually search all molecules. We have per BART, it's a fixed projection. We chose the dimensions here, by the way, to maximize what we call effective novelty. It's the percentage of molecules that are novel and valid, which would make the search the most efficient. So that's how we chose that number. And cMIM had the lowest out of them all, while having the highest ability to do that. So between cMIM and the rest, for sure. If you look here at the bottom, you can see if we limit the budgets of CMA rounds, higher is better. You can see that cMIM really shines. BART and VAE couldn't even pass after a few number of iterations, it just diverged. However, let's compare it to CDDD. That has the same number of dimensions, right? So we would expect it to be the same, but it's not. And I argue here, it's because of the structure. That clustered structure is actually lending itself to such a search. And you could see that if you have enough samples, the two models perform well, but in a low sample regime, cMIM actually outperform it significantly. So the connection to what you want to do is, you have your oracle. And to me, the most interesting part could I learn a model, just a generic principles of statistics that lends itself to many, many tasks. This is just one example. Okay, and then to me, I wanted to check if it's actually compatible with RL. And then this year, an external validation actually did that with cMIM. And you could see that cMIM actually lends itself a lot. And I would say that's time to remove this sampling and just learn the structure. It's not really required to be able to sample from any point. Any questions? All right. So let's do case study 2. This is the continuation. This is a preprint. This is still a work in progress. So it's a very, and not that, the next will be the paper, but it's out there already. And the question was, it was a great model. It was a really great generative model. But one thing bothered me. When I tried to use the latent codes, which I knew lost no information, we had almost 100% reconstruction. That means that no information was lost. But if you try to use that for downstream tasks like regression or classification, it underperformed compared to other models. And I was trying to think, how can I improve that? And the intuitive thing was, let's try to incorporate a method to improve it, an unsupervised method. And contrastive learning is pretty much a SOTA for learning today. For downstream tasks, the way that it's being done, we want each sample to be directionally separate. We're going to use the cosine similarity. You can think about it, it's going to try and spread all samples across a sphere where similar samples would be nearby. So we have a query. We're going to augment it. We're going to ask for the positive augmentation to be high if you minimize that loss. It's basically a batch weight classification. And we're going to ask everything else, the negative, to be low. And it's got complex. So we need that augmentation. Images, sure, we all know. How do you augment text? It's not clear. How do you actually do it in a meaningful way? Do you have a question?
So you said that your embedding doesn't do any information, and why though is underperforming in that data?
It's a good question. It's a very good question. I'll finish the description and then I'll try to answer you, but maybe we'll talk about it later. I can give you my hypothesis. It's actually, to me, it's very interesting to properly do it, but I'll answer it in a second. It's a good question. Yeah.
I have a clarification question. Are you learning a text encoder and an image encoder separately, or are you learning only a text encoder?
So here I'm not even talking about multimodality. I'm just talking about contrastive learning. Contrastive learning could be multimodality like clip,
Yeah.
or I'm not even talking about that.
Okay, so you're more like SimClear, like just like.
Yeah, like SimClear, exactly.
Okay, just only image.
Right now, a single, to me, the idea to test can actually incorporate contrastive learning into MIM.
Yeah.
A lot of places to move forward. Well, that's a fantastic question. Yeah.
Sorry, this is maybe moving away from where you want to go, but, you know, this is focused on contrastive methods that use both positive and negative samples, but there are contrastive methods that only use positive samples. And, you know, if you're dealing with video or language data, then there's also temporal structure. And so your positive examples could just be.
I know about triplets, I know about contrastive by definition, you have to have a negative. Is there a contrastive method without negative? I'm not aware of it.
Yeah, like BYOL, bring your own latent by Micha Valko. There's a handful of methods.
You're talking
also.
about the predictive coding?
Yeah.
That's not
Yeah.
contrastive.
Okay.
They use
They
info.
call it, yeah, okay.
They use info and see.
Yeah.
But that's not like the contrastive, I would say, method. To them, they're trying to predict how it evolves over time.
Yeah.
Yeah, it's a different thing. But yeah, there are many variants. I'm sticking here to the very basic. Okay, so A, it's not clear how to augment. B, there is sensitivity to batch size because it's a batch weight classification. There are a recent paper that actually solved it. You can do something the equivalent of gradient accumulation to have an infinite batch size. It's going to slow things down. It's going to complex things down. And it still didn't solve the issue of the augmentation. All right. So I basically introduced contrastive MIM here. And I introduced two things. A, the global separation. MIM is taking care of local structure. We have local clusters. It actually doesn't care about the orientation. So my hypothesis was that if I'm going to incorporate that, just make sure that it's spread direction-wise, it's not going to hurt it. And it actually worked well. The second thing, I'm going to switch from batch weight to expectation-based learning. So I'm not going to dive too deep into it. I think it's, if anyone is interested, we can dive to it later. But basically, I'm going to add an auxiliary latent variable. This is the proper probabilistic model, where we don't have only the encoding and decoding. We also have Q of K given X and Z. That auxiliary variable would be the contrastive. So if Z was sampled from the posterior of X, it's going to be 1. Otherwise, it's going to be 0. Now, it's a dummy variable because it's always going to be 1. That's how we sample it. But it's actually making it a proper probability distribution. And I'm going to model that, the probability of that Bernoulli distribution, given the similarity between the sample to itself. That's a constant. Anyone want to guess why don't I need to augment the same sample? Anyone want to try and guess? All right, so when you augment it, you're trying to cluster similar samples. MIM is doing it for us. We don't actually need to take care of that part. MIM is doing the clustering for us. The only part that we need to take care of is the part that's saying, be different from any other sample. And in fact, this is boiling down to the task of, you should be able to classify each sample versus all other samples. And the hope is that if you can do that, if you have some subgroups that are sharing some traits, it's going to be easier to do. Yeah, so back to your question, you asked me, you told me, why wouldn't it work? So I'm going to say it once, maybe we'll talk about it later. My hypothesis, if you have two clusters of classes that are highly clustered, and that's what you happen to want to classify, it's easy, one line, right? What happens if you want to classify some of those and some of that? It's getting harder. But if you spread everything equally, it's easy to find in hyperplane to pretty much cut almost any, not arbitrary subgroup, but any reasonable subgroup. Reasonable, I mean that they actually share some traits together. That's intuition. But it's actually worth deeper discussion and also worth deeper research. It's a very good question. All right. So the key benefits from that, it eliminates the need for data augmentation. Anyone want to guess why we don't need that augmentation here? We sampled the posterior. So we already have stochasticity in it. It works effectively well with the batch size because here what I'm asking is classify that versus all samples, and I'm going to approximate it using Monte Carlo sampling. We have a strong pack estimates that very quickly this thing would have a very small error. And in practice, even a batch of 2, I noticed very little effect. on the performance, but this is still a work in progress. And finally, it actually had minimal effect on the MIM reconstruction, which is important for us for controllability. So I'm going to quickly do two things. One is to show you what does it do. If I just take this loss, just this loss on a bunch of particles, I'm going to put it all on the first quadrant, not even around 0. It's around 1 and 1. You could see here the distribution of angles, and the radius, it's around 5. Very quickly, it's going to push it to be around 0 with equal angles to all directions. So what it's trying to do is try to spread it over a hypersphere. And in practice, the radius here could vary. It's actually, because everything is normalized, it doesn't actually affect. The radius is more important to me, to cluster things together. All right. The second thing is just to show you quickly, this would be the reconstruction loss of the same MIM. Pink here would be the regular MIM, contrastive MIM would be the yellow, almost indistinguishable in that performance. So we didn't lose much. The question is, what did we gain? I'm going to show you soon. All right, so before I'm going to show you the results, and that's, by the way, that's the end of the presentation, and we can have more discussions. I had another insight, which is, and this is going to be, might be useful for everyone, regardless of MIM, if you use encoder and decoder. If you train a large language model, and you take either the embeddings, just average them, and use that for a downstream task like classification, or you take the output of the model, just the hiddens before the unembedding layer, you average that, and you use it for classification, you will see that the output of the embedding is way more informative. It's not a bad baseline. It's not good for clustering. It's not going to be based on similarity, but it holds a lot of information. You can train a classifier like for sentiment analysis. And the question is, for me, was why? And my intuition was, at the embedding input, that represents the sample. The hiddens output, that represents the distribution over the sample. It's an autoregressive model, so the input is actually also the output, and that gives a lot more information. So let's do that with an autoencoder. But we have a problem, right?
So it's actually been done in this SSM model. So they take a EMA of the input and so you have the embedding, and they take a EMA of the embedding during. So that's how they claim to have the infinite context during.
Oh, directly of the embedding.
Yeah, like,
So the embedding has a lot of information.
decaying EMA, so decayed EMA of the directly of the output.
Yeah, and you're talking like directly after you embed the inputs, just the embedding.
Just embedding.
Yeah, so I'm not saying that there is no information either. In fact, originally when the LLM were just were discovered, they could show you that if you take man minus woman plus queen, you get closer to king.
The word vec thing. Word to vec.
The word to vec, exactly. But there are multiple researchers that show that. At least from my experience, I think that it's typically more informative to do that. But I'm not arguing that that's a ground truth. Both have been used. That's my intuition of why I did what I'm about to present. I'm not claiming it to be a ground truth. And thank you for bringing that question. It's an important clarification. You can use both. So I wanted to basically include the distribution of the inputs. The problem is that we don't have that, but we do have a decoder here. So the decoder in an autoencoder could actually allow me to approximate the distribution over the input. So if you do, you've just for any encoder decoder, I didn't test it yet, but you could test it. I tested here on, as I said, it's a work in progress, but it's a very neat trick. If you have an encoder and decoder, push your inputs to the encoder, get your latent, construct the distribution of the decoder, and just before you convert the hiddens to the parameter of the distribution, use that as your basically embeddings. Important to know that if you have an autoregressive model, you can use teacher forcing. So it's actually really, really fast, even in the case of text. And then use that. And that actually also gave me pretty much the same boost as the contrastive learning. And I'm going to show it to you. Does it make sense what I just explained here? How to extract, how to approximate the distribution over the input using the decoding distribution. All right, and this could be applied to pretty much any encoder-decoder model. You might get a freebie just for trying to do that. And it actually demonstrated improvements. All right, if there are no questions, that's pretty much the last result I'm going to discuss. Let's see, I described two things here. Contrastive loss on the latent space of latent variable model, and then the informative embeddings. So at the bottom, this is coming from the mIM paper. And as you could see, lower is better. This is a regression problem. You could see that the best model performing is the CDDD. No surprise here, by the way, this model was trained as an autoencoder with predicting those properties as a regularizer. So it actually was trained to do that. We could get close to it in different models. Seek to seek is a variable size. We just take the average. It's not too bad. Sometimes the perceiver wasn't too far. Nothing can manage to beat it. So I rerun the experiments. This first line should be identical to that. It's not because it's different code base, but you can see that the numbers are not awfully different between the MLP. I care less here about the SPM. If we compare MIM to cMIM, that's what's the improvement that we get just by adding contrastive loss to the embedding, but using the latent code. And this is what we get if we switch to informative embedding, and this is what we get if we switch to both. And again, this is a preliminary result. This is a work in progress, but it's pretty clear, A, that each contribution, either the informative embedding or the contrastive MIM, actually helps. And it tends to be that both are yielding the best result. Yeah, and that's it. So two takeaways. A, the contrastive method that's really not sensitive to the batch size and doesn't require augmentation, which is nice. The second thing, it's pretty robust to batch size. And the third thing is that you might actually be able to squeeze more of your encoder decoder just by trying to incorporate the input distribution by using feature forcing, or if it's not autoregressive, you just take the output of the decoder. Okay. Any questions about that? Any comments? Yeah.
On the previous slide on the figure, why, like this recon column, why are all those 100% and then VAE is 46%?
Because VAE has posterior collapse. That's exactly it. Yeah. Well, we try to help. So all models here, we were trying to optimize them to get the best results. VAE for text or for molecule in that case, or discrete tokens, tends to suffer a lot because an autoregressive decoder, especially the stronger it is, once you give it the first few characters, it's pretty good to go on its own. So your latent code is going to pretty much hold the information only of the first few characters. So it can be a great PDF estimator, but it's not a great, it's a very hard to control. It's not really dependent on the latent code. When you're searching in the latent code, you actually want it to be pretty much one-to-one. All right. I think yeah, all right. So we finished that. Okay, so just maybe the broader context to look back to the beginning. This work, and it's been spread, I think, over like about 5 years, different papers. I was trying to bridge between generative and discriminative models, have a unified representation learning. Having that single model good for everything is good, especially when we're getting models to be bigger and bigger and it's more expensive to train. So it's ideal to have a model that's stable to train and is versatile. Think about LLM, how versatile it is. Don't give up on native variable models, even though that's not the shiniest thing. They never went. Every multimodal model today have an encoder of the images and decoder of the images. And if you ask me, it's about to come back hard by actually starting to build hierarchy. So an LLM would have maybe a conceptual level of ideas, which will translate to sentences, which will translate to tokens. Searching in the space of ideas is going to be so much more efficient than literally spitting out. Like, if anyone here played with DeepSeek, R1? It's pretty funny to see it like, okay, the user asked me to solve that. Let me try that. Oh, wait, it doesn't feel right. Let me step back. Really wasteful token-wise. You can probably do a little bit better on a more abstract level. So conditioning on generative tasks. Again, it's an open question. What would be the best encoder? Latent diffusion models. This to me really solves, as long as you have controllable enough encoder and decoder, latent diffusion is actually a very good solution. And finally, test time inference with RL, taking a very sparse high dimensional latent space, poorly structured, and projecting it into a structured latent space here I argue that MIM latent space is useful, but there are many others. That's not the only one. Worth it. That's it. So finally, if anyone wants to talk about it, ask questions or collaborate, you're welcome. Either to try it in your thing or to explore new application. This is really just a preliminary step. I'm pushing some directions on my own, but I'm always happy to collaborate if anyone wants. That's it, I think. So yeah.
Thanks.
And yeah, thank you so much for having me. Any more questions, comments? Can dive deeper to some of the things. I know that not everyone is interested, but there is a lot of math behind it to show why it works, what makes it tick, and so on and so forth. Yeah.
I have a follow-up question. So you have intuition, and I got curious if you try to like formalize your intuition.
To formalize what, sorry?
So you have so come back to your comment that you learn perfect embedding and you can do perfect reconstruction, but
Yeah.
it underperform in the downstream task and you have intuition. And I got curious if you try to formalize your intuition into a mathematical framework.
So I'm to formalize I'm just missing that word.
The intuition.
Oh, the intuition. So not enough. My intuition, do I have a marker here?
Hopefully, is there?
Is there any? I can plot it later. I'll show you visually. I did try to play a bit with the theory. It would be super interesting for me to understand if my intuition is that if it's spread equally, you could show statistically that any reasonable subgroup would be easier to find a hypersphere to slice it. I didn't went deep enough. Like it's still an open question to me and super interesting. I actually think it could lead to very, very important insights of what makes it tick. But that would go actually apply to all contrastive. Like why is contrastive method so useful by spreading everything on direction-wise on a sphere? What makes it so powerful in downstream tasks? I think it's an important question. Oh, yeah, go ahead.
Have you tried larger data sets like image methods for this? I see mostly it's done on like SOTA and stuff.
Oh, you mean in the example?
Yeah.
Oh yeah, it's a great generative model. Here, the example I showed you is just because MNIST clusters very nicely. If your algorithm fails on MNIST, it's definitely not going to work on anything. If it succeeds on MNIST, it still doesn't mean it's going to succeed on others. So it's a good question. Yeah, MIM is like VAE. VAE can model ImageNet or whatever. So will MIM. It will just give you better control on the generation. And you need to lose less tricks and hacks to prevent the posterior collapse. You can just make, one of the nice things about MIM, you can increase the parameters and not tune the hyperparameters like weighting decay divergence, right? You can maybe truncate it. Maybe you're trying to do VQ VAE. So now you can't actually propagate the gradients, but you don't suffer from collapse. And MIM doesn't suffer from it. It didn't solve it. It's just a different framework that doesn't suffer from it. You can scale it up very easily. Yeah. All right. No more question. Thank you so much. You guys had fantastic questions. I had a lot of fun.